Hi everyone, I'm Elie. I'm from the data models team, and today I'll be talking about optimizing parallel aggregation using shared globals. I thought it would be good to start with an example SQL statement. So here we have selecting an average salary over some population, and we are grouping by some group or some column here. For example, an average salary over Massachusetts, California, etc., etc. So the state would be the column here. Now, what's the general goal? Is we want to enhance and optimize this parallel aggregation. So think any group by query that has a minimum, a maximum, an average, etc., etc. Now, how does the old implementation go about implementing this? It does it in three parts. The first one is that we have multiple workers, and each worker gets assigned a set of rows from the original table, and then they compute those aggregates, or we're going to call them an intermediary set of results, and they put them into what we call a temp file. A temp file is just a placeholder word for this sort of data structure that stores all of the data before we read it back to the user. In this case, those temp files, we're going to store the averages for this query for over the groups. So part two is that once every worker is done with calculating and processing their own rows, the set of assigned rows for them, they send back all of those results to the parent. Meanwhile, part three is where the parent is just on standby. It's waiting for the workers to send the groups one by one and then putting and aggregating or sort of consolidating those intermediary results into a final temp file that will be read back to the user. This is an illustration of how the old implementation works. We see part one has just an example worker one or worker two. Worker one gets some results for group 2, 5, 6, and 1, sorry. So think about Massachusetts, California, and Florida. Worker 2, group 6, 4, and 1. We have some overlap here. That's okay because the rows are random. Part 2 is that the workers send back those results. And part 3 is the parent process receives all of those and then processes them one after the other. Now let's consider this example. As we can see here, we can find a slow zone. For example, worker 1 sent back group 2 to the parent, and then worker 2 sent back group 6 to the parent. But what we do here is that we are processing group 1 and then processing group 2. However, if you think about it, those two groups are independent, so they are non-blocking operations that could have happened in parallel. This will cause a slow zone. As you can see, it just accumulates a lot of wait time. And if we have a high cardinality column, so we have a lot of groups, this can happen a lot, and we are going to accumulate a lot of wait time if we do those things serially. So part 3 seems to be the problem, and we want to just scratch all of that and go back to the drawing board. We start off with the set of temp files where we store the intermediary results for each worker, and then we want to end up with a final temp file. Now we want to eliminate the old part 3, which is the serial part of the parent process, and just allow the workers to write directly and in parallel into a shared global. That will be the final one that reads back the results to the user. Why does that work? Let's look on the left. We have the old implementation with the parent process, and on the right, we have the new implementation with the workers and what they're going to do. So in the new implementation, we have worker 1 is writing group 2 into the final temp file, and worker 2 is writing group 6 into the final temp file. That's happening at the same time. Meanwhile, in the old implementation, only worker 1 was writing the aggregate of group 2 into the final temp file. All of that is happening on timestamp 1. And in the old implementation, in timestamp 2 is where we delay the computation or the writing of group 6 into the final temp file. Now, on timestamp 2, we process 2 groups in the new implementation and only 1 group in the old implementation. So now look at the wait time in the grayed out section. This is getting exponentially bigger. We keep going until timestamp 4. We're done in the new implementation. The old implementation is still going, processing group 4, group 1, and now we are finally done after 3 more timestamps on timestamp 7. Now, let's look at more of a formal sort of testing for the runtime results. So we did 20 million rows. We had a table of 20 million rows, and the group cardinalities over the columns that we're grouping by ranged from 10 to 10 million. We ran the similar query 25 times, and these are the results that we got. So up until cardinality 100,000, we did not see a significant difference. Everything was within 5% in absolute value. And then after that, you see we get even better and better results the more number of groups that we are aggregating over. So in the end, we see for 10 million groups, we have about 38% increase in performance improvement. Mind you, in absolute values, the old implementation used to run this in about 40 seconds, whereas the new one is in about 27 seconds. These are more details that I skimmed over and we omitted for brevity, but a lot of things go into writing things in parallel, like concurrency issues, so we need a lot of locking on those globals and a lot of data structures. And one other good thing that is also a side effect is that the queries now are simpler because we omitted part 3 that we referenced before. So now the generated cache queries are simpler. Generated cache queries, for those unfamiliar, are basically the code that is going to read the data from the table and do all the processing to read back to the user the final results of their SQL statement. So the key takeaways is that our performance luckily improved, or at least stayed consistent. We saw a 38% decrease in our example, and the readability and the simplicity has been improved because we removed a lot of modules or steps and replaced them with a parallel setup. I want to acknowledge Boya, my mentor, and Mark, my manager on the team, because without them this wouldn't have been possible. And thank you so much for watching. I hope you enjoyed.